So welcome back to our second video. In the last video I've been talking a lot about scientific method and haven't really specified what that means in much detail. So this video is all about thinking like a scientist. Really what science is about a way of thinking. But just before we go there, let us ask, what is science anyways? So here are three pictures. Can you spot the scientist? Well, on the very left here we have someone looking very competent, looking at a lot of fancy data. I mean, that seems pretty scientific. Surely here someone mixing chemicals, wearing a lab coat. That looks like science to me. And then on the right here, well, I mean, you know, she's wearing those fancy glasses, hazmat suit, right? The mask that we all know too well by now, looking through a microscope, right? And she's got some sample under there, looking very focused and eager. Definitely science. Well, of course, in reality, all of these are actors, right? They're not really doing science, but let's pretend that's not the case. Well, are they doing science? The answer is we don't really know. They might be doing science, they might not be doing science. It depends on how they go about whatever it is that they're doing. If I just randomly mix chemicals together to see what happens, then I'm not doing science. If I'm just interested in the patterns that water makes when it freezes and I look under the microscope what that looks like, and you know, I can put on all the gear that I want, I'm not really doing science. If I just collect random data and look for patterns in it, well then I'm also not doing science. Science is a very informed way of a process, a set of practices and a set of thought processes and the way of thinking in which we go about discovering knowledge. So I want to bring you back to 1964, I think it is, and have Richard Feynman tell you about how you discover a new law of nature. Now, sadly, Richard Feynman died in 1988. Many years after he won the Nobel Prize in physics, but definitely he's one of the really big guys. And so let me tell you how he explains what scientific method is. Well, what he says is, if you want to discover a new law of nature, what you do is, you make a guess. Any guess will do. Guess something about nature. And then the important thing is, you compute the consequences of that guess. So you think very carefully, if that guess is correct, then what are all the implications that that has for the world? And then you go and you compare those implications to what nature is actually like. You can do that in an experiment, you can do that by observing data that you haven't known about before when you made your guess, that your guess is not based on. And then you check whether the consequences that occur from your guess, if your guess is correct, if they're in line with what you find or if they're not. And if your comparison to nature, if your experiment disagrees, well, then your guess is wrong. So that's the scientific method in a nutshell. It's a very simple way of explaining it. And a thing that Richard Feynman is very careful to point out is, this is all it is. It's just a guess. That's what we call a theory. This part here, computing the consequences, that's what we call predictions and hypothesis formulation. And that part here, comparing to nature, that's what we call hypothesis testing, or what we do in experiments, and so on. And then, of course, we look at the results and we decide whether our guess was right. Maybe we have to change our guess, try again. It doesn't matter if you're really smart or if you're a little bit dumb. It doesn't matter if you're really educated or you're uneducated. It doesn't matter what language you speak, and so on. Whatever people might say, it doesn't matter if you wear a lab coat or you don't, whether you sit in the library all day or whether you have a fancy laboratory with the best machinery. At the end of the day, in order to be a scientist, all you need to do is follow that methodology when you have some question about how nature works. You make a guess, you think very, very, very carefully about all the consequences of that guess, and then you compare it to nature. And if all the findings are right, then it's a vice for now, and you think about more of the consequences. And then there will come a point, very likely, where you will find that the evidence disagrees, and you're wrong. And that's what ultimately makes you a scientist. If you take that approach and you feverishly go from a guess searching to an answer that proves you wrong. So if you want to see, that talk is quite short actually. I think about 8 minutes or so. I've put the link down here in the slides, so you can click on that. I'll also put the link on the Moodle and you can go and watch that video over on YouTube. So, what is a scientific theory then? One crucial aspect of a scientific theory is that it's explanatory, right? It's not just, a statement, right? It's a guess at how something actually works that tries to explain some phenomenon of the world. So it might be that I want to explain why languages have plural suffixes and plural prefixes, but there are no languages that reverse a word to get the plural, for example. Right? I might want to explain this phenomenon of the reversal of a word from plural being impossible. If I'm a linguist, for example, it might be something else. If I'm Isaac Newton, I might want to explain why, celestial bodies attract each other, and smaller bodies on Earth as well, I suppose. A scientific theory ultimately is a model. That's something that I mentioned in the lecture video before, theories and models. Well, when your scientific theory gets a little bit more complex, right? Because you're not trying to explain one phenomenon in a vacuum most of the time, because you're trying to explain phenomena in nature that are dependent on the rest of nature. So your theory has to get a little bit more complex, and you have to start thinking about, well, lots of aspects of nature, how do I explain them if they all contribute to the thing that I want to explain? And so ultimately what you end up with is a model of what you think the natural world, or a specific aspect of the natural world that you're looking at is like, and by what rules that aspect of the world works. And a point that's very important to make, a lot of the time people talk about, explaining something. And they might even think that, well, just because, they have an explanation for something, it's a scientific explanation. But in order for something to be a scientific explanation, that presupposes that you have a theory, a scientific theory on which it hinges, namely a theory that in itself starts at smaller points, assumptions about what the world is like, has a model, and from that generates some predictions about what the world should be like, which explain the phenomenon that you're looking at. Another really important aspect of scientific theories is falsifiability, or I should rather say a really important aspect of scientific practice. So how can we know if a model is right? We might have a theoretical model that explains the entire world, but how do we know that that is correct? Well, we can never know the absolutely real laws of physics, of chemistry, or of linguistics. We are not, in some sense, if there is one, we are not God, and we haven't created the universe, so therefore we don't really know what the mathematical equations are that exactly explain thermodynamics or entropy, right? We have to make a guess. And we want to know whether our guess is correct or not. And so if we can never step outside the real world as we're part of it, then we have to think about how we can discriminate good guesses from bad guesses. And what you've seen before already, what Richard Feynman so eloquently said, if it disagrees, it's wrong, right? If it disagrees with nature, it's wrong. And so to know about this disagreement, a model has to be testable. And that means it needs to be clear what data or what observation we could make in the world that would tell us that we're wrong. This is what we call falsification, right? So a good scientific theory, right? Scientific theory is qualified by the fact that it's, a guess that explains something. Okay, fair enough. But if I cannot test that theory, then it's useless because I can never confirm whether it is very likely to be true or whether it's very unlikely to be true. So in order to have any chance of filtering out good scientific theories from bad scientific theories, or correct scientific theories from incorrect scientific theories, I must be able to test this in the real world, and for that my model must make clear predictions about what observations or what data or what experimental results would falsify my theory and tell me that I'm wrong. Because only then can I go and look for that data to see whether I'm actually wrong or whether I actually might have a chance of being correct. So let's move on then. What's a linguistic theory? And that's a term that you'll be confronted with a lot over the next 10 weeks, and then in term 2 another 10 weeks, and then in your dissertation you'll be thinking about that non-stop. So what is a linguistic theory? Well, a linguistic theory is a theory that explains why certain linguistic phenomena occur. So, for example, the restrictions and plural formations that exist in the world's languages, or even the way plurals or superlatives, right, good, better, best, work in a language like English, right? What is it that speakers know and that they have in their mind, and how the mind works, that ultimately gives rise to those patterns and restrictions and the knowledge that we find people can acquire and the knowledge that we find people cannot acquire. So that's what a linguistic theory is in principle. And just like with scientific theories, there could be, a good or a bad linguistic theory. There could be a linguistic theory that's falsifiable or one that's unfalsifiable. So what is a good linguistic theory? Well, a falsifiable theory that explains why certain linguistic phenomena occur. A good linguistic theory, in other words, makes specific predictions about what phenomena are and aren't possible. So let's illustrate this a little bit, and we'll hold off doing linguistics for a while yet. In the next video, we'll take this, what we've learned here, and then we'll apply it to some linguistic data. But just to be illustrative, let's just have a little bit of fun and ask a fun question like, where do maggots come from? Right? This is something that you're probably familiar with. I mean, in the time before we had refrigerators, this was a much more common occurrence and something that people probably wondered a whole lot more about. But it's an experience that you probably can empathize with. You have a perfectly good piece of meat, and you leave it out for a few days, and then maggots appear. Right? That's a phenomenon. That's something that happens out in the natural world. And so people have been thinking about that for quite some time, it turns out, right? In the 1500s, 1600s, and so on. People have been thinking, well, where do maggots come from? And they came up with a theory that is called spontaneous generation, right? And it's an explanatory theory. So basically what they said is that, well, when meat rots, and we don't understand why rotting happens yet, some chemical process, then maggots are generated. So, in other words, maggots are the result of a chemical process that happens in the meat. Right? This is the meat generates the maggots while rotting. Right? Whatever happens when rotting occurs, right? Those chemical processes lead to the creation of maggots. Right? This theory is called spontaneous generation. Right? It's clearly an explanatory theory, so by that token it's a scientific theory. Right? It's a gas. But is spontaneous generation what we call a good theory? So have a moment to think about that. Well, yes, it is. And why is it a good theory? Well, it's a good theory because it makes testable predictions and therefore is falsifiable. So let's go and see what that might look like. Right? So to test spontaneous generation, we have to think about the implications that this guess has. Right? Compute the consequences. So if we compute the consequences, or in other words, think about what that guess implies that the world will be like if our guess is correct, right? If maggots are generated through the process of rotting in the meat, right? Then what else should be true about the world? And, have a little word of caution here. It's very, very important to make a distinction. What we're thinking about here is not what the theory claims is happening, but what it implies that's happening, that it's not explicitly saying, right? The theory claims that maggots appear spontaneously on meat when it rots. Well, that's an obvious fact. That's just a way of restating the very observation, right? But it implies that that will happen in certain ways. So we might say the claim is that maggots are generated by rotting meat. But the implication of that claim is, or one of the implications of that claim is, that maggots would still be generated if the meat was isolated from the rest of the world, right? If no human and no animal and no bugs and no insects were to touch that piece of meat, as long as it rots, maggots should still appear, right? That's an implication of that theory. And so from that implication, right, we can derive a scenario that should be true that we can carry out in real life. So that's what we might call a hypothesis. So our hypothesis here is, well, if we seal the meat in a container so that nothing can get to it and the meat is isolated, right, while it's still unspoiled and perfectly fine, then the maggots will appear when the meat starts rotting. Right? Since they come from within the meat, they generated, like, everything that is needed for the generation of the maggots is already there, right? As long as the conditions are met for rotting, and we know that meat rots even when, we put it in a container, then, the maggot should still appear. So our hypothesis is we put it in a container, the maggots will still appear. And this is actually an experiment that has been done in the 1700s, in the 1600s, 17th century. So Francesco Redi was an Italian naturalist, biologist, right? He's proclaimed to be the founder of experimental biology in many ways. And he was wondering about this theory of spontaneous generation, and he thought, well, that can't be right, right? He was one of the discoverers of what is now known as germ theory, right? The fact that lots of little animals and stuff have an effect on the world and are active in things decomposing, causing illness, and so on. So what he did basically is he took 2 jars and a piece of meat, and one of them he put in an open jar, and another one he put in a jar and then covered it with cloth. Okay, so you might think, well, I could just put a lid on it and close it completely, but it actually turns out the rotting process is slightly different, and then people would criticize you for saying, well, maybe the maggots are dying before they come out of the meat because they need air to breathe, right? And so a way to get around that is you say, well, I put a cloth over it that, to my knowledge at the time, in the 1600s, no animal or bug, right? They weren't able to see the germs yet. They didn't know about germs. Can get through. So it's isolated for all intents and purposes, but it still has access to meat, right? You can breathe through that piece of fabric. So then you put them there and you wait for several days and you see what happens. And of course, in the jar that's open, flies and gnats will get to it. And what he found is that maggots appeared on the meat. But in the other jar that had cloth covering, where no flies and gnats could get to the meat, no maggots appeared. And in fact, he took that a little bit farther, and then he removed the cloth covering, right, after those several days, and pretty much in a couple of hours after he removed that cloth and flies had landed on it, maggots appeared, right? But so this very fact, just this scenario here, having these two comparative things, right, and the latter one is the one for our prediction. The first instance here we might, say is something that we use as a control, right, just to make sure there's nothing wrong with the piece of meat that we have, for example. So maybe, for some reason it doesn't rot properly, but it's the same piece of meat, right? We put it in different jars, so we know it's not the meat. We can exclude various factors. We're pretty sure at this point, well, what made the difference is whether, bugs and grubs and flies and gnats could get to it or not. So the findings disagree with the hypothesis, right, with the consequences that we computed from our guess of spontaneous explanation. And as Richard Feynman says, if it disagrees, it's wrong, right? So that's how the theory of spontaneous generation was falsified back in the day. Right? That theory is wrong, we have to throw it away. We could go back and make, modify it, make additional guesses and add conditions, right? And perhaps that would be an initial step. If I just closed it off, I would say, well, maybe they need air to breathe, right? But eventually that theory dies out and other theories make a better explanation. And their results agree with what we find in nature, right? For example, we later then found out, well, these are actually the eggs, the larvae of flies and gnats, right? And so that is a much better explanation. Okay, so let's summarize what we've been looking at here, right? So scientific theories seek to explain something. That's the most important characteristic of them. Scientific theories, on a very simple level, are just guesses, but they're a specific type of guess. They're not simply a vacuous statement about the world or how something is, right? I could claim that, UCL is the heart of London's academic community. That's, neither falsifiable nor does it seek to explain anything, right? So therefore, that's not a scientific theory or scientific guess, right? It's a guess of some sort, but it's not the kind of guess that we're looking for. So we're looking for guess that explains something, right? That's what a scientific theory is about. And a scientific theory must make clear predictions. If my theory is so vague that I don't know where it goes, well, I can make vague theories all day long, and nobody can ever prove me wrong, and nobody, and I will never know whether I'm right. And that's how a lot of conspiracy theories work, for example. Then it's just completely useless, right? It doesn't really explain anything. Because the very fact that I'm trying to explain something means I need to make a clear prediction about why that phenomenon is the way that it is, right? And so if I'm being vague and imprecise in formulating my guess and writing it out and sharing it with people and, maybe even in thinking about it myself, well, then I don't have a scientific theory by definition, because I'm not making any predictions. And now, if I have a good scientific theory, well, then it makes predictions that I can actually go out in the world, do something in the world to find new data, to make new observations, to check whether it agrees with nature or not, right? So it's falsifiable. And, to sum up then this idea of scientific methodology, right? Scientific methodology is a set of practices, really, right? A way of thinking and going about making guesses and checking whether they're true, that serves us in developing, refining, and selecting good theories, or perhaps deselecting good scientific theories, right? Spontaneous generation is a good scientific theory, precisely because we could reject it very easily, right? But it happened to be wrong. So that's what that really is about. And this is also why, and you see, I step back in front a little bit. because it's a habit of speech to call it the scientific method. But a lot of people actually that work in the philosophy of science and that practice science try to avoid putting the definite article there, because it gives you the idea that it's just one set way of doing things, but that's really not what it is. Really, scientific methodology is very diverse. There are very many ways to arrive at the guesses. There are very many ways to arrive at predictions and consequences that they have, and very many ways to check for the results and confirm them and disconfirm them and select a better theory or worse theory and so on. So it's really a set of practices, and therefore the preferred terminology is really to call it scientific method rather than the scientific method. So I promised you the last time that I would tell you why. Okay, so lastly, let's get back to linguistics. And last point here, remember, a good linguistic theory then is a falsifiable theory that explains one or more linguistic phenomena. And we're going to try and come up with some good linguistic theories just in the next video.